Alright, pre-calc. So today, as long as we have our calculators, we're going to talk about matrix solutions to linear systems, and they're definitely the easiest way, again, as long as you have a calculator that we can plug it into. Okay, so what we need to do in order to solve this and learn how to write an augmented matrix, and then use our calculators to solve this with something called reduced row echelon form, which you will see in your calculator under math as RREF. Okay, so to start, what an augmented matrix means is we're going to create a matrix that is created from a linear system, and we're going to use that to solve the system, and it's made of the coefficients and the constants of the systems. So a matrix is going to be some set of numbers that we put in brackets like that. So we could have 2, 4, 5, 6, -1, 0, 8, 2, 4, 3, 2, and 0. And this would be what's called a matrix. And we talk about rows by columns. So we'd say that this is a 3 by 4 because we have 3 rows and 4 columns. This would also represent a 3 variable systems of equations. Like these would be your x coefficients, these would be your y coefficients, your z coefficients, and then this last column is going to be your constants. Okay, so to create an augmented matrix, like we just said, isolate the variables and constants on opposite sides. So all the variables on one side, all your constants on the other sides. We're going to create the matrix with a vertical line separating those. So this vertical line is like your equal sign. And then finally we're going to solve the system using our calculator, and this really is what we're going to talk about next time in class. So this video is going to be all about the first 2 steps because there's quite a few detailed steps for this one. Not hard, just make sure you want to get it right. So to create an augmented matrix, you already see that your variables are on one side, your constants are on the other side. So we're going to make our big bracket, and now we can just write our equation. 3, 1, 2, 31. I'm going to put my other bracket over here. X is 1, 1, 2, and 19, and then 1, 3, 2, and 25, and we can put a line down this. Now, there's been a couple ways. If those of you who've seen FST, you've probably seen this done a little bit differently. In my opinion, this is the easiest and quickest way to do it instead of doing 2 different matrices and then finding your inverse. So once you've created your augmented matrix, it's just a matter of plugging it into the calculator, running the RREF program, and it'll do it for you. What you'll get is something that looks like this. And this is a good thing that we want, because you'll notice we have X, Y, Z, and then constants. So this first line is an actual equation where we have 1x, no y's, no z's, and a constant equals -5. So this tells us that x equals -5. The second one tells us that y equals -2. And the third one tells us that z equals 9. So we have one solution for those 3 variables. If we change our matrix a little bit, you'll see that this says x equals 6, y equals 3, so we think we're good. But now this says 0 equals 5 because there are no x's, no y's, no z's. This is not true. So actually here we would say no solution. Okay, another option could be that suppose this one actually said 0 here. So then, because if we're thinking in red, this would say 0 equals 0. That is a true statement. So we would say that this actually has infinite solutions. So there's several different options. We could have where just x, y, and z are some number, simple, easy, done. We could have an option where we create an untrue statement like we had in black here, 0 equals 5, not true, so no solution. Or a completely true statement with no variables defined, everything 0 equals 0, and therefore we have infinite solutions. Okay, we'll talk about how we create those matrices tomorrow in class, but that's basically the gist of it and how we put those in our calculator. If you can create an augmented matrix, you can very quickly and easily solve a linear system of equations for as many variables as we have. See you next time.